Let's start. Hi, everyone. Good afternoon. Are you ready? Okay. I put the chat. 20%. Oh, we lost a lot of people. So it's not good, this. 20 participants. I start to be less famous than Sarat. 21. Okay, we start at 22. We start at 22. Good, perfect. I don't know who was the last one, but okay. Can I see some people? I don't see the people. Where is the view option? Okay, thanks. I can see one. Okay, we can start now. So, okay. Alors, so I see one student, and now I want to hear another student. And we start. Another student. I want to hear a voice.
Hello, Benoit.
Hi, Peter. Okay. So we have it's quite a big week for you this week. A lot of lectures, a full week, one assignment. So congrats to everyone who have submitted yesterday. Don't be stressed for the quiz on this weekend. It will be an easy quiz. 4 questions and it will be easy, just to see if you have well understood the contents of our lectures. So no stress on the quiz. Okay, so today we have 2 hours in a row, so 50 minutes, a break, 50 minutes. You have, I hope everyone got the slides from the website. So you should have all the slides for the 3 hours. And also I put also some illustration on some specific point of what we'll see today. Okay? Okay. So we can start. You can see my screen or not really. Not really see. Yes. Can you see my iPad or not?
Not yet.
Not yet. Okay, it's not share anymore. Okay. Why? I will put again. Share. Come on. So we have a lot of stuff to see, but it's not really. We need to do step by step. And if we don't see, if we don't have time and to see all the slides, no stress. We come back later on. Okay, so the first part of the lecture, it will be a review of the shallow network, very fast. And after we will go through the full neural network. And with the matrix representation of the full neural network, I will provide you some activation function and the derivative of the activation function. And we will back again on the backpropagation on a simple example. Okay, the second part of the lecture today will be the backpropagation on the deep neural network. And we will see how to compute derivative with which called the automatic differentiation. And after a very important point, it will be to see that a deep neural network can approximate any nonlinear function from mapping from the input to the output. And an important point you have seen yesterday is on the optimization, it will be the weight initialization, in fact. And tomorrow we'll go to some regularization technique to overcome the issue of the overfitting which is quite common in machine learning and especially in deep learning. Another approach to deal with this trouble on overfitting is called the dropout. We will see also the importance of the batch normalization and some intuition about the vanishing gradient problem. And we finish on Friday by a tutorial. We can do a summarize of all of this we will see today and tomorrow. Okay, so back to what we have seen as the first lecture. So the formal neuron has been introduced in 1943, in fact, and is just a mapping from the input X to the output Y. And you have the first mapping, which is a linear part with the linear combination of the features with the weight W and the feature X plus a bias, which is called also the intercept in statistics. And after you applied on the second part in your neuron, an activation function. Most of the time is non-linear, but it could be also a linear activation function for regression purpose. So what we have seen at this stage for regression task, when your outcome y is a scalar, so is living in R, the activation function is the identity function, which is the most natural. And this we have seen that is equivalent to a linear model, which is expressed by the expectation of y given some information x. And it's just a linear combination of the weight and the features. For the binary classification task, we have seen that when our outcome is a binary response, so generally in the logistic model, we coded as 0 and 1. And so we use the sigmoid function, which is a nonlinear function. And on the linear predictor X transpose W, so the linear combination of the features with the weight. And this is equivalent to the logistic model. I made some small typo in the chapter. I think I corrected, but someone sent me an email that I missed maybe when I show the relation between minimizing the cross entropy and it is equivalent to maximizing the likelihood minus the log likelihood. And I think maybe a factor of 1 divided by n. I need to check again if I keep a mistake on my notes. Okay. And on the multi-class task, is just a concatenation of k for all neurons, and the activation function is called the softmax, and you get a nice exercise on the assignment. So I think it was exercise question 5, or you have shown that the optimization function based on the cross entropy for categorical variable is a convex function. Okay, so this is what we have seen at this stage. And what we have see also, which was a little bit surprising, is that the logistic and the softmax model produce linear boundaries. And I hope that everybody are aware about this. And I think in my first lecture, I show very quickly that for the logistic model, you end up with a linear boundary decision for classify the 0 and the 1. Any question about this point? You remember this point? And I hope that everybody is comfortable to show that a logistic model, so a sigmoid model without any hidden layer, give you a linear boundary decision. You're comfortable with this point? Yes, okay, thanks. Okay, and so what is the solution to get something non-linear as decision boundary is in fact to add a hidden layer. So instead to go directly from the input and connect all the input together in one neuron to get the output, we will add one hidden layer. You see this hidden layer, and this will help us to get something non-linear for the input to the output for the decision boundary. So I think I show you just an example and I will explain after for this. So I saw a short demo. So I think for the short demo, we need to go through another file, which is nonlinear boundary. Do you get this file? So don't be scared about the R code. It's just to some people, if you want to reproduce this example, you will be able to reproduce this example. So I'll let you a little bit some time to get this file. You have this file? I want a yep. Where is the file again? Peter asked to everyone. So on the website, you should be able to see the file. So the file, if I show you where is the file, where is here. So if you're going there on this website, you need to do a good job. You organize well all the file. So there you should be able today to see that, where is it? Where we are today, we are.
Might need to refresh it.
Yes, it's true. I haven't. Okay, yes. So you are there, you have slides, and after you have approx overfit nonlinear. Make sense, Peter?
Yes, thank you.
Okay, so now I got the file. Where is the file? Is here. So what I have done, I just have simulated some fake data, but a nice spiral. And so we have two classes, the, let's say, green and orange or red. And we want to classify this, to build a classifier, to classify these two shapes. And based on just two features, X1 and X2. So I just run first a logistic model. So it's just a GLM. So in R it's called GLM for generalized linear model. And I got this linear decision boundary based on my logistic model. So you can see that it cannot separate well my two groups. And now I just had one layer. So I use, just for people who know R, but people doesn't know R, not a trouble for this. I just use the library Neuron net, and you can see that just in one line of code, I just put my two features, X1 and X2, my data. Hidden 4 is meaning that I just had one hidden layer with 4 neurons. And what I like this nice function, that we can plot the neural network. So you can really understand where are the weight and the bias and how many parameters you have to estimate. So in our case, I will ask you as a question to see if everybody is sleeping after lunch, or listen to me, how many parameters in this model? When I ask this question, I try to count also for me.
There's 2 parameters.
Okay, 2 parameters. So now we'll do a poll. Who is who are agree with Christina? Thanks, Christina. Okay, so Jade said 12. Peter said 17. Matt said no. So we need to work on it. It's good. So Christina, what was your parameters you were thinking? Maybe the language.
Sorry, I looked at X1 and X2. I just realized it's 12. Is it 12, 13, 14, 16?
Okay, so X1, X2 is just the features, covariates.
Yeah, I realized I mixed those two up. It's
okay.
17.
17. So everybody says 17. So we have how many bias we have? 1 for each neuron. So 4 for the first hidden, 4 bias, and 1 bias for the last neuron. So it's 5 bias, yes. And after we have 12 weight. So 4 for the second part and 8 for the first part. Yes. So we have a model with 17 parameters. And now this model maps the 2 features to the Y. And if I plot the result based on the cutoff, because this model gives me also a probability, a predicted probability. So now if I have a new point on my space, so I have X1 and X2, I feed in my model and it gives me as output a probability. And based on the cutoff, I will decide if it's green or red. So if I'm doing this, you can see that, oh, it's quite nice. Isn't it nice? Oh, okay, I was thinking it's nice. Just by adding one hidden layer, what is the metric? So I want to know more about, I can reply to your question, but I'm not sure if it's the question I will reply is about the question. Metrics. So I will say the loss function is still the cross entropy. So my weight have been estimated by using the cross entropy. Okay. The matrix, I haven't used any matrix. Matrix is, when I say matrix, is to judge, to evaluate the quality of my model. But I haven't judged any matrix. I just represent visualize. But it's a good point. I could, based on this model, if I want to compare, to know I can compute the F1, the accuracy, and so on and so on. I have replied to your question, Jade. Okay. So I was just wanted to play a little bit more with this. I add a second layer to see what is going on. So I add a second layer. So I have my model is more complex. It has the capacity to approximate some more complex relation between the input and the output. And I just visualize. So I had just 2 hidden layers. So now I have my neural network is 2 hidden layers. So more parameters to estimate. And if I look at the result, it's quite nice. So now I have managed to classify my nice picture with the green and the red. So just the information I wanted to tell you here is keep in mind a logistic model, a softmax model. If you just, okay, this is a question of Sarat to everyone. And after I will reply, is this a overfit?
Would we need to use this neural network on a set of testing data to find out whether it was an overfit?
Yes, so we'll see later. Yes, you're right. I just have here, it was just to show the capability of a neural network to get non-linear boundary decision for classification. So this is my way to highlight this. So I just did this on the training data, but of course you can do a validation test and optimize your model on the validation test. And after, check on the test set. So we do this later. So I haven't done this, and I haven't compute the metric on the test set, but at the beginning, I think I split my data in two. Yes, I split my data. You can see in train and test, but I haven't used the test set. But I just wanted to show you this, and we can do this later, and we do this during the practical. Okay. Yep. Okay, back to the business now. So this was the highlight. I wanted just to highlight this point. So I come back to the slide. So now you know that when we add one layer is going to something nonlinear. Okay. So we have done this as the first part. It's called the one hidden layer neural network. And I just put the equation of the hidden layer network. So the equation is with this notation. So you have, yep. You have Z1, Z1, Z2, Z3, Z4, which is from the first part, Z1, Z2, Z4, and this notation is for indicated the first hidden layer, okay? And you have for each neuron, so replicate, in fact, no concatenate. So for each neuron, you have this on set of weight, which is denoted by W underscript 1, 1, a linear combination plus the bias, and after, on this, you apply an activation function. And so the output on this, in A, so from this arrow, the output here is quite, you see this. So we do this. The output, oh, not this, okay, this one. So the output here is A1, which is a scalar, okay? And this one, this is A2, which is a scalar. This is the output of the first of each neuron. And these four outputs are combined with a linear combination to get to go to the last neuron, which is here. And this one is computed by the linear combination of, you can see first the linear combination of the four output from the activation function on the first four neurons plus a bias, and you get the Z1, 2 because it's a second layer, which is just the output layer, and you applied the activation function of this Z1, 2. Is it pretty straightforward? So we go slowly, but just to be sure that we are all in the same page. So all good for everyone? Okay, this is a good question. Matt asked if sigma is the same for both layers. So the most common, they don't have any reason to, we can have a different sigma event for each neuron, but is never done for this part. We just use the same activation function for the hidden layer, but yes, Matt, when you add a layer, and especially in this case, as is output layer, the output layer is the activation is really depending the task you are working on. So, for example, if we use a regression task, the activation function, this one, should be something like the identity. But if you are doing classification, it will be the sigmoid. Make sense, Matt? Yes, good point, Jade. So the first part, what I like when I on this each time the neuron is like this, you can see. So when you enter in the neuron from another part, all of these arrows are combined with first part is a linear combination, and you have a bias. And the second part, you applied an activation function, which most of the time the activation function on this part is nonlinear. Make sense, Jade? Okay, so keep in mind, each time is always the same. The neural network is you arrive in a neuron, you combine all of these elements as a linear combination. Okay, it gives you a scalar plus the bias. You applied an activation function which is R to R, and the output is a scalar. Sarat asks many questions, but we go to this, Sarat. It's good. Sarat asks, what happens if there's a linear combination? So I can ask this question because I think I already put this information on the website. So everybody should be comfortable to reply to the question to Sarat. So the question of Sarat is say, okay, I do linear combination, linear combination, linear combination. Yes.
Thank you, Benoit. Just to make sure that.
Yeah, it's a good point. It's a good question. So it's good because Matt reply, the whole thing is linear. Yes, because in fact, is when you do a linear combination, is as you is the algebra, you apply it's like you multiply by a matrix, and so is a matrix multiplied by a matrix, and in fact is going by a composition of linear function which is linear. Yes, we use linear function just as the identity, I would say identity activation function just for the output layer, for just the output layer for a regression task. Because if we have a regression task and we want to estimate something which is living in minus infinity and plus infinity, we need an activation function which is not bounded. Yes. Good. Okay, I stopped my. Why I stop this? Okay. Share again? No, tell me no this mistake for me. Sorry. I will share again. Share screen. It's good. We have plenty of questions. Okay. Keep going. I don't see if there's some question now. I lost the chat. The chat is here. Okay, perfect. Okay, so now we can, of course, in mathematics, we like matrix because it simplifies the reading and the writing of all the equation. So in the chapter, we have just this, use the matrix notation to help us to write more compactly the equation of the neural network. So here we have the information. One new message. Okay, I hope. So the network should be take. Okay, good point, Jade. At this stage, it's true that when you do the forward now, I just did the forward for one sample. But with the matrix notation, of course, we will go through all the sample. Okay, and just some how to write this and how to code this. But keep in mind also that what you have seen yesterday with Sarat, for the optimization problem, sometimes is not, if your sample is huge, it will be too time consuming for doing the forward pass for all the sample. And we keep in mind that we do some mini batch. So it will be some subset of sample step by step. So we need to write the equation for one single sample, because sometimes we just go through one sample. If you do the full stochastic gradient descent, is one by one. But if you do the mini batch, you need to write this forward pass for a subset of samples. And if you use the full gradient descent, you need to for all the samples. Okay, so now is the matrix notation. Matrix notation, I might tell you that I did sometimes some mistake with notation, with transposition, and so on and so on. So we need your work is to check if this notation makes sense. So now I have written this with the matrix notation, which is where W1 for is the weight for the first part, so input to the first hidden layer. And after you have W2, which is the weight for going from the output of the hidden layer to the last layer. Okay, so you have to, in our simple neural network, we have two weight matrices, W1 and W2. Okay, so I put this matrix. I hope it is fine. And I think I have some question to keep you awake. Oh, and I have a question, but Sarat asked already the question because he wants to be fast. Why nonlinear activation is important?
Sorry, Benoit.
So we can see that Sarat didn't do the good job of a student. He haven't go through the slides before the lectures. So why nonlinear activation is important? So if I just do a simple neural network and I consider a neural network without activation function. So meaning without activation function is the same as identity function as activation function. And if you write this, you go through this, you can see that W2, the weight W2, the second part of the weight, will be multiplied by W1, is matrix. And these two matrices will form a new matrix, which is W new. And you can see that is a linear combination of the new weight and the bias. So, in fact, doing a linear combination with many layers, we don't exploit the advantage of a neural network to get something nonlinear, and we don't exploit the power of the neural network to approximate any nonlinear function. Okay? So just keep in mind, summary in red, linear activation function is used for the output layer in case of regression. Okay. So now we go to the point of today, deep learning with N layers neural network. So not just one hidden, but many hidden layers network. So how it's working, it's quite simple. It's just to do some bricks. So you just add some bricks of neural network. And it's just on some cascade of layer. But there are different kind of architecture, and sometimes simple, sometimes sophisticated, is depending your task you want to achieve. So today we will concentrate on the multi-layer perceptron. it's the oldest one and the simple one. And next week, you are going to work with Yoni on convolutional neural network, which is specifically designed for mostly for image processing. And later on, we just have some flavor on recurrent neural network, which deal with sequential data, like some temporal data, and also is also used a lot in text for text data and for language processing. So like translation and so on. So we'll see this later. Okay, so some definition, what we call many names for the multi-layer fully connected network, which is called also the multi-layer perceptron, or also called the feed-forward neural network. So I put an image here. I think I steal this image. I don't remember who was the property of this image. I apologize. So the multi-layer network is a cascade of multi-layer, and with each is a nonlinear transformation. So it's fully connected is because you can see that we have here in this example, we have two input and it's connected at each neuron at the beginning. Why I can do more? Oh no. Ah, yes, it's here. Okay. So this is connected. Each neuron input is connected to all the neuron, and each output is also connected to all the next neuron. You can see, and this output, for example, is connected to all the neuron, and so on and so on. So this is the reason why it's called fully connected, and it's a feed forward because it's going in this direction, and you don't have a connection from one output which is come back, for example, there. And we will see that this kind of network are possible when you deal with recurrent neural network. So, but at this stage, we just go forward. So it's a feed forward neural network. Make sense? Okay. So it's easy to extend what we have seen by adding more layer in cascade. So I just write here the forward pass equation. I'll let you just some second to read this equation. And here I have used the matrix notation. So in this equation, W with the script 1 is the weight from the first part. So if I come back here, this in fact is, I will say, is all this weight. So this is the weight for W1 here. And the second there, I can see, I hope you see, this is all the weight for the second part. And so on and so on. Okay, for the notation. The B corresponds to the bias, so it's also a vector, depending on the number of neurons. And you have also, I call this GR for the activation function at the layer R. And an important point, nobody asked, it's good, but I think the number of neurons in each layer could be different, not necessarily equal. I don't know if you can see that in this example, the first island had 4 neurons, this one had 6 neurons, and after 6, 4, and 1. So you have the forward equation. Yes, but I would say yes, Mathematically, I would say yes, but by experience, I never seen a code with a different activation function. But I can, because it's maybe more complex to program and to code, but it be possible. But most of those is more frequent to have the same activation function at each within a layer. Okay, now we have, it's sometimes a little bit tricky when I come in this field, is to count the number of layers in a deep neural network, because there are the input layer, do we count like a layer, the output layer, do we count like a layer, and so on and so on. So the consensus is when you counting the layer, we count the hidden layer as well as the output layer as a layer, but the input layer doesn't count like a layer. Okay, question to Peter, which is important, and we'll go through. I will reply to your question. I finish here, and after I reply to your question. I ask you a question on this. I have some question mark. It's not some mistake. Is a teaching purpose. So you need to feed this this question mark. So this neural network, is it with Yes, perfect. Okay, everybody got it. Perfect. So it's a 4-layer neural network, and in fact, there are 3 hidden layers. Yes, we can say this, Matthew. Start to be deep when is greater than 1. Yes, we always count the output layer as a layer. Doesn't matter of the activation function. Okay, I come back to the question. We try to help the question, which was a question from Peter. In the weight matrix, is each rows of the weight for each neuron or the weight for one of the input? So, for example, we go through an example. It will be easy. So, in this example, the first matrix is this one. What is the dimension of my first matrix? I have 3 input and how many output? 1, 2, 3, 4, 5. So I don't remember which is a 3 by 5 or 5 by 3. I don't remember. Yep, 5 by 3. So I put 5 by 3. I don't remember which way I put the W. W multiplied by this, X is in this dimension, so it's P by 1. No, is, yes, is wrong. Yes. So it's P, so the entry, the column is P. Okay. Yes, you're right. 5 by 3, agree. Okay. And yep. And for this one, can you tell me? It's good point. W, this is W1, W underscore 3. What is the dimension? Everybody agree with Jade? Jade, I think you missed something. Jade, the 5 by 5, it was this one. 5 by 5 is this one. Okay? Yep, good. 3 by 5. Perfect. Okay. So now it was a question at the beginning from one of your students. He asked us if we do this one sample by sample. So now we can vectorize this across the multiple training example. So keep in mind that we have m sample, m data points. Okay, each data point have d features, but we have a sample size of m. So we need to do at the end m prediction for m data points. Make sense? So we need to have to feed our neural network at the end. So we can also use a matrix notation. So I put all the data in X. So in X, you have all the data. And you can see in my notation is one of the notation. You can see if you look at another textbook, maybe you will have the transposition of this matrix. So you need to see this not like a black box. You need to understand what is going on, because sometimes people will use X, sometimes people will be X transpose. It depends also the language and so of programmation. So in my notation in this, I have used each column is one sample. Okay, is one data point, one subject, for example, or one image if you want. So I stack this in column like this, by column. And after you can go through all of this because it's not the main point, but and after you can write this for all the sample. So this now is quite summarized for the M training data. You have these 4 equations for our model here. For the first example, or the second example. Make sense? 2 minutes after the pause. Oh my God. Okay, so you need to, as an exercise, I will not do now. I'll put you on the example here. You need to feed this. And when somebody has feed this, I will put the solution if somebody send me this. Okay? So it's the dimension of each object. It's good to work on this, because if you work on this, you will think about the matrix and this, and maybe you will see I did a mistake. Okay, so this is for you, dimension summary of the component. And now we need to just talk about a little bit of activation function. Starting at this point, do we assume that the X matrix just contains the input? Yes, exactly. No?
Sorry, I just mean for the dimension summary, are we assuming that each layer has the same number of neurons to estimate those dimensions?
No. We take the notation MR. So I say, maybe I say, here, look.
Oh, okay, yep, sorry.
No, not be sorry. It's going fast, a lot of information. Don't be sorry. So it's a good question. It's a good question. Okay. So MR is the number of neuron in the layer R. Okay.
Sorry, I'm still a little bit confused. It's
Yes.
probably just me not understanding. But so if you look at the picture that you've shown us with each layer color coded, so even assuming that you only feed in that first X1, none of the other data points are fed in, so none of the other mathematics, none of the other neurons are being lit up. That X1 still feeds one value into 4 separate linear equations, which
Yes.
will give out 4 outputs for that second layer. Sorry, 5. But then all of the arrows connecting to each of the neurons in that first layer are then activated. So that's 5 linear equations feeding into each neuron in the second layer. So do the activations for the second layer take the sum of those 5 linear equations, or?
Okay, I will precise this. Let me know if I'm not clear, okay? I will do a zoom to be clear. Look, I'm doing this. I take this one, okay, this neuron, and I explain this neuron A. Okay, so this neuron is like this. There are 1, 2, 3 arrows with coming on this neuron. Make sense? X1, X2, and X3. Tell me at once when something is not clear, okay? Is okay now?
Yeah.
Okay, first part, you can see each neuron like 2 parts. First part is going inside, and he will compute. I don't put the good notation, but he will compute X1, W1, plus X2, W2, plus X3, W3, plus the bias.
Okay.
And this gives Z1. But
Okay.
Z1 is not just now, just one value, okay? So this part is just one value, Z1. Make sense?
Okay. Okay. So there's one bias term attached to each neuron, not one bias term attached to each arrow.
No. Just, yes.
That's, yeah.
So,
Okay.
yes. And after this Z1, you compute A1, which is an activation function on Z1. But A1, so the output on this neuron is A1 here. So you can see this is A1.
Okay.
And on this A1, you have an arrow which coming, we are going to another neuron. And on this one, you will have a new W here.
Okay. Awesome. All right. Cool. Thank you.
And each time is the same. Okay? You
Yeah.
repeat this process each time, but it's just the weight we change. The bias and the weight change. This gives you the flexibility to approximate well a new function. Is clear?
Yeah. Yeah. Awesome. Thank you.
Okay. So I offer you is on your course, and the course are very generous. They offer you 10-minute break. Okay? See you at 4? Okay, see you at 4.
Thanks,
Nobody?
Benoit.
Yes, okay. See you at 4.
See you, Benoit.
Yeah. You know, it's my time of my push-up, huh? Everybody need to do some exercise, huh? Okay.
Say again?
It's time for the push-up.
Yeah.
10-minute push-up, huh? I want
Yeah.
some sweat. Okay, see you soon.